Okay, welcome to Chapter 3, Section 6. So we have worked through a bunch of material, understanding all of these linear things. This time we want to look at certain relationships. So we're talking about proportional and non-proportional. So that word is long, but the idea is simple. So we'll look at what those things mean, understanding it, and using it in some problems. So one thing to look at and understand is how a proportional relationship looks in a graph. So in words, we can say here a relationship is proportional if its equation is of the form y equals kx. So we've seen this before, just like our direct variation stuff. K can't be 0, and it always passes through the origin. So proportional will pass through the origin here. So here's an example, y equals 3x. This is also in your book. So notice the line goes through the origin. There's nothing else being added or subtracted here, so you could imagine there's a plus 0, but there's nothing there. It's just 3x. And you could plot some points here, and you'd see how they change. The ratio of x to y is constant. And you see a line going through the origin and up to the right. It has a positive slope of 3. So that is proportional since it goes through the origin. So we'll look at some graphs that look like that. So first we have 1a. This problem has some context about energy. So it shows the number of miles driven for each hour of driving. So after 1 hour, it's gone 50 miles, 2, 100, 3, 150, 4, 200. So we see that there's a pattern there. They ask us, now I need you to just have the table. So just write down these numbers. Forget the words, write the numbers in the table. We want to have a graph for this, so we'll draw that also. And the question asks us, what can we deduce from the pattern about the relationship between the number of hours of driving used with the variable h and the number of miles driven? We'll call that m. So we want to know what's happening between these two variables. So if we plot these points, we get a graph like this. Now please have this down. And looking at these points, we see there's an upward trend to the right. And if we wanted to connect those with a line, we would see it goes through the origin and up to the right. And we could figure out the slope of that thing as well if we wanted to. So what do we know about the hours and the miles? How are they changing together? Well, their relationship is linear. Linear, since this would form a line between these points. So it's linear between the hours of driving and the number of miles driven. Those two things change the same way in a constant way. Because notice a line is straight, it doesn't bend, it doesn't curve, it keeps going in the same trend. So that's it for 1a. We want to understand that yes, this is proportional because it goes through the origin. So it is proportional. And it is also linear because it forms a line. So those two things, proportional and linear. So make sure you have the table and the graph as we finish this context energy problem and move to the next one. So part B asks us to write an equation to describe this relationship. So we know we have the graph and we have some points. So we could use those things to now find out what is the equation of this relationship. So write an equation. Well, what equations do we know that deal with lines? We know we want to understand the relationship between our x values. You can call that the domain. And our y values, you can call that the range. We want to find a pattern. So let's look here. So the hours are increasing by 1 each time. The miles are increasing by 50 each time. So what would that tell us as far as our slope? Well, we know our slope is the change in y over the change in x. So how is y changing? 50. And how is x changing? 1. So our slope is 50 over 1, which is just 50. And that's miles per hour. So our slope is 50 miles an hour. So to write an equation, we would know the difference of the values for m is 50, we said. H is 1, that's the changes here and here. So this tells us that the number of miles is equal to 50 times the number of hours. Because every hour that goes by, you get 50 more miles. So there's our slope that we found, 50, right here. Times the number of hours gives us the miles. So we can check to see if this equation is correct by substituting values of h into the equation. So please have the table. Don't worry about the words. You already have the table from last part. So be sure to have the slope and our equation, m equals 50h. As we move to the next slide. So we can check to see if this is indeed true. If h is 1, what do we get? Well, plug in a 1, we get 50. Is that a point in our table? Yes, it is, 150. So if we plug in a 2, what do we get? Well, 2 times 50 gives us 100. Is that a point in our table? 2, 100. So yes, those work. We could do the same thing with 3, and that checks out. 4 does as well. So we know our equation is indeed correct. So what do we know about the answer? M equals 50H is the right formula. So you should already have that down for this problem. Now, 1C. We're going to use what we found to find some predictions. So we can know about what might happen in a hypothetical scenario. So using this equation, we can predict the number of miles driven in 8 hours of driving. So 8 is our number of hours. That's our h in our equation. We know our equation given is miles equals 50h. So how many miles will we have gone? How can we find that? We plug in for h right here. They tell us it's 8. So where there's an h, we replace it, and we'll substitute in and get that value. So there's the original. With one step, we get 8 times 50. And multiply that through, you get a nice even number, 400. So in the context of the problem, how many miles did we drive? We would drive 400 miles in 8 hours given our original equation. So have 400 miles for 1C. Now 1D. So we're looking at a different relationship here. Please have down the table. Those values are important. So looking at this data, we want to know what conclusion can we make about what's happening here between the miles and the time spent walking. So we've got hours as our x, miles as our y. We know we can track how these things are changing. So let's look at that. So as the hours go up, they're going up by 1 each time. And I'm only going to put it here once. So the change in x is 1 between each value. What is the change in y between each value? Well, it looks to me like it's going up by 1.5. So remembering that our slope is delta y over delta x, we know that the change in y goes on top. So which one is y? Y is miles, 1.5. Remember that trick I told you that x is always some time value? If you have a time value, it's going to be x. So that'll let you know which one's y and which one's x. So the hours are increasing by 1 each time. So our slope is 1.5 over 1. And we know anything over 1 is itself. So our slope is 1.5 miles per hour. So that is our slope. Now, what else do we notice? We know that these things are changing in a constant way every time. So what can we say about this relationship? Well, we know that it has to be linear, right? We worked on solving problems like this before, where we said, are the changes always the same? If they are, it's a line. If not, then it's not. This one is an example of it definitely being linear because the changes are constant. We said it has a slope of 1.5. So we know it's linear. So anything that says nonlinear, we can cross out. So B is wrong. Now we said we know it's linear. So looking at the available choices, only one of those makes sense. And we know it has to be A. So this is a linear relationship between the number of miles walked and the time spent walking because they're increasing at a constant rate for both variables. So have linear relationship down for 1D. So 1E, using the same info we already had, we can now write some kind of equation to let us know how these things can be written in a way that we can use to make some future predictions. So given this info, we said we knew the slope was 1.5. So we should be looking for this number in our equation. Now, what does that 1.5 tell us? We know the number of miles can be predicted by 1.5, there's our slope, times what? The number of hours. So let's check that. If we went for 1 hour, how many miles should we get? Well, 1.5 times 1 would be 1.5. Is that a point in our graph? Yes, it is right here. If we went for, let's say, 4 hours, what would we get? Well, 4 times 1.5 would be 6. Is 4, 6 a point in our table somewhere? Well, yep, it's right here. And we could go through and check any of these points that we want to, and they would be true with that equation. So we just checked to see, is this equation true? And it exactly is based on this info. So of these choices, we know C is the only one that is correct. So there we have that described. M equals 1.5H for 1E. Now, this is the third part of the same data. So we have the table already. We have our equation now, which I'll rewrite. So we have that convenient for us. So given this equation, what can we do now to make a prediction? So we'll just substitute whatever they give us. So they say, use your equation, predict the number of miles driven in 8 hours. So there's our given. That is going to be our H. They want us to find out the miles, M. So what is M given 8 for H? So where does that take us? Well, with just one plug-in, we can get there. H we know is 8. So the number of miles will equal 1.5 times 8. Now the question is, what is 1 and 1/2 of 8? Well, if you have 1 times 8, that would be 8. Plus half of 8 would be 4. And 8 and 4 together, added as a sum, would be 12. And you can multiply that out to double check. So how many miles went by in 8 hours? How far did they go? 12 miles. So we know B, C, and D are out. A is our solution on this one. All right, so we worked through a bunch of example 1 type problems. So we have a couple example 2 to look at. So notice the red marker up here tells us we're now focusing on situations that are non-proportional. Non, the prefix, meaning not proportional. So Looking at A, it tells us write an equation for the graph. So we're given some points. We can try to write an equation for what's happening here. So there's a few steps we need to do to get there. So first, let's understand what we're asked to do. We need to somehow get to an equation. And we know our relation is graphed in front of us, so we'll try to find that equation. So plan, how can we understand what to do next? So we know we need to find the difference in the x and y values. In other words, how are these things changing? What is the slope between the points? That's something we'll definitely need for any equation, right? What is the slope? So, please try to have this image down. It doesn't have to be exact, just so you can have something to reflect on. Notice this one does not go through the origin, so please be sure it doesn't on yours. So, if we take the points in the graph and make a table, we would get this here. So these values are important for this problem. We can then look at how it's changing. So as we increase from one x to the next, we're increasing by 1 every time. As we increase from one y to the next, we increase by 3. So now, what do we know? Well, we know our slope should be change in y over change in x, which would be 3 over 1. They're both positive. So our slope should be a positive 3. So notice in our little paragraph here, given we just found the slope is 3, this would suggest, meaning maybe, our equation is y equals 3x. So this is true that it does have a slope of 3, but we don't know for sure if this is the final equation. And I'll tell you, anything that is non-proportional is going to have some kind of a plus or minus after your slope. Only things that perfectly go through the origin are nice and neat like this with nothing else after it. We already talked about how proportional ones go through the origin and they have nothing else added. So y equals 3x would be proportional. We're talking about ones that are not. So there's more to do. So if we were to check that equation, we said y equals 3x. If we were now to check that equation and see if our points line up when we plug in values, we can double check to see if this is true. So if x is 1, we would get 3 times 1, which is 3. That's what you see here. But the y value for x equals 1 in our table is 1. So if you go back, when x is 1, y is 1. We didn't get 3, we got 1. So that's not true. We're 2 under what we should have gotten if y was going to be equal to 3x. So we can try some other value to see what happens. So this is a table of these values. Now I don't expect you to write this, but do try to understand it. So our x values are given here, our y values are given here. This is what we're going to get out in our equation. Now we thought y could equal 3x, but if we notice these values are not the same, right? But there's a pattern here. If we compare these two, we compare the y values to the 3x values, what we thought it could be. How are these different? What is the pattern between each of these? Well, the y value is always 2 less than whatever 3 times x is. You see that here. It's always 2 under. So since this is true, we know our equation. We thought it could be y equals 3x, but we just found each y value is actually 2 under that. So we'd have to add a minus 2. So this now is our actual equation. Y is equal to 3x, take away 2. So that is one way to find that equation. And if they ask you anything weird like function notation, what does that mean? Change the y to f of x. That's all that means. F of x and y are replaceable with each other. You can switch them out. That's it. Leave the rest. 3x minus 2. Then you're done. So we can write an equation for this example as well for what is graphed in front of us. So I'll tell you that the method we just showed is one way to do it. Another way to do it is to find your slope first. So how do I find the slope between any 2 points? Well, I'll track the change in y over the change in x. So change in y between these 2 points, it goes up 2. And x, it goes over 1. So my slope is 2 over 1, or just 2. So my slope is 2. Now the second thing we need to have in order to write our equation is a y-intercept. So what is my y-intercept? Where does this line cross this y-axis? Well, where does it cross? It's below. It's on the left, left, left. It hits here, and then it's on the right. So where does it touch? Right here. And what is the y value at that point? Well, it goes up to 1. So b is 1. So I know my blank equation would be y equals mx plus b. M and b we just found, so we can substitute those in. So y equals 2x plus 1. Now they asked us to change it to function notation. So with one last step, just change the y to an f of x. And f of x equals 2x plus 1. So which of our answers gives us that? We know it has to be D. So for 2b, try to have yourself an image of the line crossing at 1, going up to the right, and we found that with a couple steps. So you should be okay to solve some problems as we jump into some practice time.